single. Chroma means color. So that's why the definition what we can give for monochromatic nature is the source which contains single wavelength or frequency is called monochromatic source. So the source which we are going to consider must have a single wavelength or single frequency. I hope you know what is wavelength. Wavelength is the distance between two adjacent troughs or adjacent cracks, or the distance between two similar points. Right? So it should have a single wavelength or single frequency. Then only we can call it as a monochromatic source. So the examples of monochromatic source are laser, as well as the other thing what we know is sodium vapor lamp. Now let us compare the monochromatic nature of sodium. This is our laser source, and we are comparing this with our sodium vapor lamp. So here let us consider the helium neon laser whose wavelength is 6328 angstroms. So this is for helium neon laser wavelength. And coming to the sodium, what is the color of sodium? Which gives yellow color and whose wavelength is 5893 angstroms. So, as for our definition of monochromatic source, what is the condition? It should have a single wavelength. That means if you draw a graph between wavelength versus intensity, what should we have? We should have a single line at 6328 angstroms, as well as a single line for 5893 angstroms. So that is what is our expectation. But what is happening is the line spreading is taking place. For laser, the spreading is del lambda, wavelength spreading is approximately 10 angstroms. And coming to the sodium, that is plus or minus 500 angstroms. From year to year, plus or minus 500 angstroms. So when you compare the line width, del lambda is 10 angstroms for laser, whereas del lambda is 1000 angstroms for sodium vapor lamp. So that means 1000 by 10. So what is our conclusion is laser is a better monochromatic source. How much better? 100 times a better monochromatic source than sodium vapor lamp. Right? Then the next thing what we want to study is coherence. How we can define coherence? When there exists fixed and predictable phase relationship between two photons, then the source is said to be coherent in nature. Right? So what is the condition? There should exist fixed and predictable phase relationship. So phase, already we have come across one of the properties of wave. So if you look at wave properties, a wave should have the following properties. One is amplitude, second wavelength, third phase, fourth intensity, and the fifth one frequency. So these are the properties for a wave. So what is so this is a wave, and this is its mean position, and the maximum displacement from the mean position. This displacement we will call as amplitude. And already we mentioned wavelength is the distance between two adjacent troughs or two adjacent crests. So this is what is we call as wavelength. Phase means you see for this wave it is 0, pi by 2, pi, 3 pi by 2, 2. So even we can talk about the phase of a wave in terms of these. And coming to the intensity, the square of the amplitude is called as intensity. And lastly, what is frequency? So this we will call as one oscillation, and number of oscillations made per second is called frequency. So a wave should have all these properties. Now in this discussion of coherence, we are interested in phase relationship. If two waves are going to maintain same phase and the same amplitude, then that is said to be coherent in nature. So in terms of definition, when there exists fixed and predictable phase relationship between two photons, they are said to be coherent in nature. Or in general words, if two waves maintains same phase and same amplitude, they are said to be coherent in nature. Coherence is of two types. One is called temporal coherence, the other one spatial coherence. What do you mean by temporal coherence? Coherence with respect to time. Whereas spatial coherence is the coherence with respect to position coordinates. You see, this is a Cartesian coordinate system. This is our x-axis, this is our y, and this is our z-axis. So this is observation point whose coordinates is x, y, z. So here the point of observation will not change, but time t1, t2, so on. So at t is equal to 0 seconds, we will look at this point. So what is passing through that? A crest. And after 5 seconds, again a crest is passing through this point. At 10 seconds, again a crest is passing through this point. That means with respect to time, always we are getting a crest at this point. That's why this kind of coherence we call as temporal coherence. Coherence with respect to time. And coming to the second one, spatial coherence. So again, let us take the coordinates x-axis, y-axis, and z-axis. So this time, what is fixed? Time is not going to change. Observation time is same. But where do we observe these things? We are observing at x1, y1, z1, and x2, y2, z2. So now, if you look at this point at the same instant of time, what is happening here? Through the both points, what is passing? Across. So here they are maintaining the same phase or a fixed phase, and predictable phase relationship is existing between these two photons with respect to position coordinates. That's why it is called as spatial coherence. The question is how long they will maintain the same phase and same amplitude is called its coherent length. And the case of helium neon laser, the coherent length is 600 kilometers. So far we concluded that ordinary light is chromatic in nature, whereas laser light is monochromatic in nature. The second difference is ordinary light is incoherent. There is no relation between one photon and other photon. But coming to the laser, there exists fixed and predictable phase relationship between two photons. And now look at the third parameter. What is that? High directionality. Ordinary light is divergent, whereas laser light is directional. So if you see, we have a satellite which is able to focus 1 kilometer. It is also spreading 1 kilometer. So what is happening here? The photons are not going to maintain any fixed relationship with them. But coming to the laser light, what is the condition just now we completed? They must maintain same phase and same amplitude. That's why all the photons that are emitting from this laser light must maintain same phase and same amplitude, or in other words, they must be coherent. Because of this coherent nature, what happens? The all the photons are confined to a unique direction leading to high directionality. So laser light is highly directional, whereas ordinary light is divergent. Right? So if you able to focus a 10 centimeter dia laser beam from Earth to Moon, it will spread 5 kilometers after reaching the Moon. What I mean to say is, so compared to the distance traveled, the spreading of 5 kilometers is nothing. So that is the power of laser. Laser is highly directional. And the last one is high intensity. So if you take ordinary light, the light coming from the photons radiated from the ordinary light are diverging in all directions. So that's why they are less intense. But just now we realized that all the photons are confined to a unique direction. Because of the coherent property, all the photons are confined to a unique direction. So the number of photons available per unit area, is very large, so leads to high intensity. So the number of photons available per unit area is very high, leading to high intensity. So let us conclude what we have learned in this. So first thing, let us try to find out the difference between ordinary light and laser light. So first, what is the first thing? Ordinary light is chromatic in nature, whereas laser light is monochromatic. Second, ordinary light is incoherent in nature. Laser light is coherent in nature. Third difference, ordinary light is divergent, spreads in all directions. Laser light is highly directional. And the last one, the ordinary light is less intense, whereas laser light is having high intensity. So from all these characteristics, we can conclude that laser light is superior than ordinary light.